Okay, so welcome to this session of NCTS Algebraic Geometry Seminar. So today we're very happy to have Xiaolei Zhao from UC Santa Barbara, and he's going to talk to us about non-commutative abelian surfaces and Kummer type hyperkähler manifolds. So yeah, please
Yeah,
go ahead.
thank you. Yeah, thanks for the introduction, and I want to thank Flora for inviting me to speak. Actually, I was invited to speak in the conference that's going to happen next January, which unfortunately I couldn't make, but I'm sure it's going to be a lot of fun. In any case, thank you. Yeah, I was planning on just speaking about this recent work in progress with on the thing basically in the title. Let me just make sure. Can people see my shared screen reasonably well? Is that all right?
The title is kind of small.
Yeah. So let me try to write something, and then
Yeah.
so if so let's say this is joint work with Aaron Beyer. Is it big enough?
Yeah, this all
Okay,
right.
great. Yeah.
Thank you.
Alex Perry and Laura Pertuzzi. And let me just mention from the beginning that I'm going to throughout just work over C. And just also to make sure people can just ask questions, right? Just talk through the microphone and
Actually, can you make your screen horizontal? Landscape.
horizontal. Okay,
Yeah,
let me
that would be.
try whether I can do it. Oops. Let's see. Maybe like this. Oops. Maybe like this. Is it better?
Yeah. This is
Okay.
much better. Yeah.
Oh, good.
Thank you.
Okay. Yeah. So and people just stop me whenever you have question or anything. Hopefully, this is as close as possible to like a real talk in a classroom. Okay, yeah. So let me just directly start introducing the kind of moduli space I want to really somehow study or more like generalizing. So let me start with the first part of my talk, which is about the abelian surfaces and also the so-called generalized Kummer varieties. So generalized Kummer varieties. Okay, for the rest of my talk, I'll call this kind of thing GKV. Okay, so let me actually just write down the definition. So I'm going to fix a polarized abelian surface, maybe as a pair A and H is the abelian surface and H is a polarization. So the following construction, which is more or less due to Yoshioka generalizing previous work. So if I'm taking a primitive class V in the algebraic part, in the algebraic lattice of this abelian surface, okay? And what I mean by this is that so I'm just looking at H0 direct sum the part on the narrow subary. So it's like H11 intersect H2Z, and then direct sum H4. So if I fix a vector in this lattice that's primitive, so in concrete word, I'm just fixing the rank, the first Chern class, and the second Chern class of this class V. Then in particular, I can take the moduli space of H semi-stable sheaves. So this is actually the moduli space of H semi-stable. Let's assume my polarization is generic, and in this situation, I get actually only stable sheaves of Chern class V, let's say. Okay, so this is actually my moduli space. It can be constructed classically, and there are a lot of study of this. So for the purpose of my talk, I have to modify this moduli space a little bit. So I'm going to take the Abunazi morphism of this moduli space to its Abunazi variety. And in this concrete situation, the Abunazi variety is isomorphic to A cross A hat. And this particular Abunazi morphism can be given by the determinant due across the determinant. So the map to the second factor is taking the determinant of the sheaves and parametrizing. And the first factor is like via taking, for example, the firm chi of this sheaf and then take the determinant of that. So in any case, this is actually going to give me a non-trivial morphism which coincide with the Abunezi. And so I'm gonna actually just define my KHV to be the fiber of this Abunezi morphism, say over the origin. Okay, and this kind of thing is what I will call a generalized Kummer variety. This is my GKV. Okay, so this is actually the first thing, and it's somehow a good exercise to convince yourself, like when you plug in the simplest character, this will actually just recover the Kummer K3. But then when your moduli space is of a higher dimension, so of dimension at least at least 4, then in particular this construction will become isotrivial, and then you take the fiber. This fiber is going to give you an interesting hyperkähler variety. Okay, so let me actually just quickly write down the next definition, and then I'll say a little bit about hyperkähler variety. So when I say I have a Kummer type, I say I have a Kummer type hyperkähler. Manifold. So what I mean by this, so hyperkähler manifold. So what I mean by this is that I have a deformation of the previous constructed JKV, and I want a polarized deformation, so deformed as a projective variety. So it's a polarized deformation of GKV. Okay, so I deform this thing into some other projective variety, and I'll call this kind of thing Kummer type. Okay, so maybe I should just really give some background on this hyperkähler manifold, and like which kind of examples at this moment we have. So I say I have a hyperkähler variety X. So in particular, I mean the following. So let's say this X has to be smooth projective variety satisfying the following two conditions. So the first is that if I look at the H20 of this thing, so, this is actually going to be just it's kind of generated by a section eta, and moreover this eta, I assume this is actually a symplectic form. Namely, it's nowhere degenerate. Okay, so this, in particular, the such a eta will actually trivialize this H20. Okay, so this is the first condition. And the second condition, I'm just going to assume that if you, for example, consider the analytic topology of this complex variety and look at the fundamental group, I assume this is simply connected. Okay. So in particular, if you think about the surface case, the first condition is really just telling me the canonical line bundle is trivial. So in particular, you have either K3 or abelian surfaces. And the second condition will rule out the abelian surface case. And so for surface, the only thing you can have as hyperkähler is actually just K3. Okay, so what are the examples that we have? Well, not much. So the first type of example would be something called the K3n type. Okay, this is really something like I can actually take, for example, Hilbert scheme of n points on K3. Or more generally, I can take a moduli space of H semi-stable sheaf with some kind of class on K3. These are examples of my K3 type hyperkähler. And in this situation, you can already see, so they allow actually some kind of non-trivial deformation that doesn't a priori come from K3 surfaces. But indeed, this deformation are still projective hyperkähler manifolds. Okay, this is actually one type of thing, maybe the first type of example people came up with. And the second type is really the thing I mentioned before at the beginning, so this Kummer type. So you can start from abelian surfaces, which is not hyperkähler, but we'll just bring this thing to a higher dimension, and you just do this Abunezi construction, Abunezi fiber construction to kill the fundamental group, then this is actually going to give me something simply connected with a symplectic form. Okay, so this is actually the Kummer type. And then beyond this, actually, there are two more kind of isolated examples in dimension 6 and dimension 10, constructed by O'Grady. Usually, this are known as OG10 and OG6. So the picture here is like I start with a moduli space of sheaves that's slightly singular. But in some very special situation, I would be able to resolve the singularity and still get actually a hyperkähler manifold. Okay, we're good. Yeah, so this is actually basically all the smooth projective examples we know at this moment fall into one of these categories. Okay. Yeah, so this is some kind of background on the hyperkähler. So let's come back to this Kummer type thing. So I want to actually quickly state several facts about this Kummer type hyperkählers. Kummer type hyperkählers. Okay, so the first thing, so if I view this as actually a polarized variety, and I just study, for example, the moduli space or the deformation space, so these things all come inside the four-dimensional polarized moduli. If I fix them a polarization and I look at the polarized moduli of this type of thing, they are always coming in four-dimensional moduli. But on the other hand, if you look at the previous construction of the generalized Kummer, so this depends on choosing a abelian surface, and then I fix some kind of discrete data, just the class. So in particular, this kind of generalized Kummer construction deforms when your abelian surface deforms. And then in particular, that's like at most a three-dimensional family, okay? But only three-dimensional loci inside this four-dimensional polarized moduli, only three-dimensional loci can be actually constructed as GKV. And indeed, actually, there are also other ways to say this. For example, you can verify that all the things that can be constructed as generalized Kummer variety has Picard number at least 2. But on the other hand, the generic deformation in this moduli space will have Picard number 1. Okay? So the generic ones don't really come from a moduli space of stable sheaves on a abelian surface. Okay, so this is actually one thing. So another thing, this is actually just a fairly recent work due to O'Grady. So actually, if you look at the third intermediate Jacobian of this kind of Kummer type hyperkähler, now in this situation, H30 is actually 0. So H30 of this K is always 0. So this is the nice situation that the intermediate Jacobian becomes actually just a abelian variety. So this is by definition now the dual of H21 quotient of the lattice given by H3Z. Okay, so I'm integrating all the 2-1 form and then quotient out the ambiguity that's coming from just the periods of all the things on H3. Okay, so then in this situation, the polarization gives you abelian fourfold. So this is an abelian fourfold. Okay, but indeed, this is some kind of very special abelian fourfold, so-called abelian fourfold of weight type. Okay, so I mean, towards the end of my talk, I'm going to actually introduce the definition of this thing. Okay, but for this moment, I think maybe the only thing I want to mention is that so this type of abelian fourfold is interesting for one of the reasons is that there's actually a non-trivial Hodge class on this kind of abelian fourfold, which we can just write down by linear algebra. But on the other hand, the Hodge conjecture for this Hodge classes remained open for many, many years until the recent work of Markman, in which he completely solved this. Okay, so so let's say maybe I'll just write here. So Markman proved the Hodge conjecture for this type of generalized for this kind of intermediate Jacobian, this type of abelian fourfold of weight type. So let me say that so this is the first paper of Markman on the subject, in which he proved for this kind of intermediate Jacobian, which has some kind of discriminant 0. There's a certain invariant which is 0. And then in a more recent work coming from maybe just a couple of months ago, he actually proved this thing, the Hodge conjecture for abelian fourfold in full generality, which is the only remaining case of the Hodge conjecture for abelian furfels. Okay, so yeah, I'll come back to this kind of thing at the end, and then I'll basically say like what our kind of categorical moduli method can say for this type of questions. Okay, so but before I continue, so let me actually make a remark. So you see that I've been talking about like the polarization on this kind of generalized Kummer variety or something. So from the moduli point of view, actually there's a very concrete way to really produce polarization. So let me say, explain. So what's the polarization on this KHV? Remember, this is the Abolisi fiber of the moduli on the abelian surface. So this is also basically due to Yoshioka. So if I look at the second cohomology of this HV, this can be identified with the orthogonal of this character V I started with inside the even cohomology of this abelian surface, say with the integral class. Okay, and this is actually compatible under as a polarized Hodge structure. There's a Hodge structures on both sides, and there's a natural polarization on the left-hand side given by BB form and so on and so forth. Okay, but all what I need is that so inside this H2, I have the class of the polarization. Okay, so under this isomorphism, this is actually going to just correspond to some class W that's going to be orthogonal to my V. Okay, so basically this polarization is really just given by some integral class that's orthogonal to my V. This isomorphism is in some sense just a variant of the Donaldson isomorphism for moduli of sheaves. Okay, but let me just say this much, and so in our later construction, we'll also need this W, which should be thought as somehow a way to give me a polarization on my generalized Kummer variety. Okay, yep. So this is actually maybe some kind of background on this on generalized Kummer variety and their deformations. Let me pause for a second and see whether there are questions. Oh, good. Okay, so yeah, so what do I want to do here? So for the second part, maybe I'll just state my main result. Okay, so before I really say what I want to prove, let me just maybe give like a slogan or kind of the general philosophy behind the thing. So the thing is that although the general element in this moduli space, so this moduli space will be actually four-dimensional, while the ones coming from moduli spaces are only three-dimensional. So that means the general element in this moduli space are not from moduli of sheaves on abelian surface. But the slogan here is that in some sense, I can define a non-commutative deformation of an abelian surface. I'll call this in polarized non-commutative deformation of this abelian surface V, of this abelian surface A, and this will actually give me all the polarized deformation of generalized Kummer varieties. Okay, so there will be some kind of non-commutative deformation of A that somehow we don't really see as an algebraic variety, but you'll see like we'll see this thing as actually some kind of triangulated categories. And there's a way to formulate a moduli problem on this, such that when I take the moduli space, those are precisely the generic member of that four-dimensional family. Okay, yeah, so this is actually just sometimes a slogan. Let me make this precise by actually stating the main theorem. This is going to be actually a long statement. So let me fix actually abelian surface A. I fix a class V. This is the one that I use to form the moduli. And I fix a W, which is in the orthogonal of V. This will be the one that's giving me the polarization. So I claim just start with this data, this A and V and W. So there exists a family of triangulated categories triangulated categories. Let me call this in curly A over a 4-dimensional base. Base B with the following conditions. Okay? At this moment, it's just kind of a family of triangulated categories over some 4-dimensional base. So the first thing is that, like, this has to deform this A I started with. So there will be actually a base point in this B, such that when you restrict to the fiber of this family of category over this base point, this is really just the derived category of A. Okay, and by this I mean the bounded derived category. The bounded derived category of coherent sheaves on this abelian surface A. Okay, so this is my notation, D of A. Okay, so this is the first thing. And sometimes I have actually a deformation, a 4-dimensional deformation of this the derived category. Okay, so the second thing I would say that this V and W remain algebraic. Okay, in this whole 4-dimensional family. So by this I mean that there's a way to actually talk about the cohomology or the lattice of the cohomology of this in this setup, this abstract family of category. So basically, I just mean that there are classes, there are objects inside the triangulated category whose topological classes are precisely my V and W. Okay, they can be realized as the class of some object in my category. Okay, so this is the second thing. So V and W remain algebraic. Okay, so moreover, I claim there exists a family of stability conditions in the sense of Bridgeland stability conditions. Let me call this thing sigma on this family of category A. So basically that means there on each fiber there's a Bridgeland stability condition and they somehow come in a compatible way. So I will say a little bit more what I mean by Bridgeland stability condition. So what's the definition of this thing in a second. But for the moment, let me just say that Bridgeland stability condition in particular allow me to talk about the moduli space of semi-stable objects inside this triangulated category. Okay, so in particular, in this situation, for every point inside the space, so if I take a point, if I take a point B inside the base, so I can talk about the moduli space with respect to this Bridgeland stability condition at this point of objects inside this corresponding category of this class V. Okay, so part of the theorem guarantees in this situation, this moduli space is not going to be empty. So I really have actually a non-empty moduli space, a projective variety. And moreover, the Abernethy morphism, so the Abernethy map of this projective variety is actually going to map to a 4-dimensional abelian variety. Okay. So the situation is very similar to what I said at the very beginning. So if you take this abelian surface, this A, and here H, this polarization H is in some sense just replacing the stability condition. It's like a special case of the stability condition. Then I can actually take this moduli space of H stable sheaves of class V, and the Abernethy morphism is actually a morphism to A cross A dual. So this is A cross A dual would be the abelian furfold. Then sometimes I'm really in a kind of a generalized situation that's very, very similar to what happens over this fiber, over this point 0. Okay. And moreover, if I take the fibers of this thing, so I'll just similar to before, I'll call this thing K. This is with respect to the stability condition, the category, and so on and so forth. They are indeed Kummer type hypercalars. Hoover-type hypercalars with actually polarization. So far I haven't really used this W. This W is used to really make sure like there's this polarization that induced by this class W. Just as I mentioned before, like via this Donaldson morphism. Okay. So in particular, there's a four-dimensional family of Kummer-type hypercalar that coming from this four-dimensional family of abstract triangulated categories with stability condition and class. Okay. And finally, what's the upshot? The upshot is the following statement. This is the last statement in this theorem. So every general Kummer type, general means general in their moduli, general Kummer type hypercalar arises this way. Okay, namely, it can be realized as actually a moduli space of stable objects on a triangulated category. Sorry, the Abernethy fiber of that moduli space. Okay. Yep. So maybe this is the moment to just introduce the terminology. So you see that I have this four-dimensional family of triangulated categories, as I was saying here. So each fiber of this, so each triangulated category inside here is called a non-commutative abelian surface. So if I take a point B and look at this triangulated category at this point B, this is what I mean by a non-commutative abelian surface. Yeah, non-commutative in the sense like it's categorical. Okay. This is a triangulated category that deforming the derived category of an abelian surface. Okay. Oops. All right. See, there's some question.
Yeah, so maybe is it possible to characterize these non-commutative abelian surfaces just in terms of the properties of the triangulated category? Or?
So I can tell you some properties. So for example, this thing is 2 Calabi-Yau in the sense that there's a Serre functor on this, which is just shifted by 2. This is somehow very similar to the Serre duality on abelian surface or any K-trivial surface. There's roughly a way to talk about this cohomology, like Hausdorff cohomology or whatsoever, and that's the same as those of abelian surfaces. Okay, but if you ask that you take a smooth proper triangulated category with all these properties, whether they are really one of the things I constructed here, I'm not sure I have a good answer to this question.
Okay, I see. Thanks.
Other questions? Okay. Yeah, as I promised, maybe I'll just say a quick word of stability conditions. Okay, so this is kind of like just a remark on what I mean by stability condition. So let's say I have actually A, this is a triangulated category. So stability condition sigma on this triangulated category A consists of the following two data. So the first thing is called the heart of the T structure. So I'll just write A heart. And the second thing would be actually the so-called central charge, and I'll write it as Z. Okay, so this A heart, this is the so-called heart of a bounded T structure, actually. T structure on this A. Okay, so in particular, this is actually some kind of abelian category. So if you think about the derived category of coherent sheaves, so one typical T structure can take is really just take the abelian category of coherent sheaves, viewed as complexes that concentrate in degree 0. Okay, so in particular, this is actually going to be an abelian category, and so basically, I won't really say too much about this, except that this roughly gives me a way to consider what's actually a coherent sheaf in this case. Roughly, this tells me which kind of coherent sheaves I'm looking at in this case, rather than complexes of coherent sheaves. Okay, so in particular, this is an abelian category. And inside this category, I can talk about sub and quotient, so that all those things will make sense. Yeah, so this is the first part of the data. I have actually a hard of T structure. And the second part of the data is actually the so-called central charge. It's really just from the numerical Grothendieck group mapping to C, mapping to the complex plane. And so in particular, you can just imagine that whenever you have actually a, let's say this is a complex plane, whenever you have an object, E, in this category, they can take the class of this thing in the numerical case, in the numerical Grothendieck group, and the central charge would actually just map it to a point on the complex plane. Okay, and once I have this point, in particular, I have actually a slope of this complex number, which roughly tells me what I mean by the slope of an object. Remember, in classical definition of either slope or G-Seeker stability, I need some notion of slope of a coherent sheaf. The central charge is in some sense replacing the notion of slope in this story. Okay, so the first thing in particular tells me what's actually, sub and quotient object, and second tells me what's slope. So in particular, once I have these two things, I can define what's semi-stable, just as Euro. Semi-stable means all the sub object will have actually a slope smaller or equal to the original object. Okay, and so on and so forth. Okay, yeah. So I mean, this is a extremely rough kind of sketch of what I mean by stability condition. So the whole point here is like it's a theory that in particular allows me to talk about semi-stability and the moduli of semi-stability of semi-stable objects and things like that. Okay. All right. Okay. So this is actually just the long statement of my theorem. So I have a family of triangulated categories such that if I take the corresponding moduli space of stable object with class V, that really gives me this four-dimensional family of the generalized Kummer varieties that I want to understand. Okay, so yeah, so this is the main statement. So for the rest of this talk, I want to actually explain maybe two things for the rest of the talk. I'll explain two things. So the first is I want to explain like how working with triangulated categories instead of varieties allows me the flexibility to really prove the theorem. Okay, so how working with triangulated categories gives me the flexibility to do this. Okay, I won't expect this thing to hold like I have a four-dimensional family of abelian surfaces. That's just not going to happen. And the second thing is that I want to actually explain the application of this thing to the story I was telling at the beginning, to this intermediate Jacobian story. So in particular, so from this perspective, it gives actually a very transparent explanation why the intermediate Jacobian has actually a wave-type structure. Okay? So these are the things I will actually try to explain for the rest of the talks. Okay. Yeah, so this is maybe just the main theorem. Okay, let's see. Pause for a second to see whether there are questions. Oh, good. Okay, so let me actually start by maybe just the first thing, and I'll explain a little bit of the construction. So this whole theorem is really just a construction of this four-dimensional family. Okay, so I'll start by doing this thing. I'll start doing this thing by just recalling a very classical story between surfaces. So this is the relation between abelian surface and Kummer K3. Okay, so the starting point is just to recall that actually this Z mod 2 acts on any abelian surface, any abelian variety, by just the plus or minus one. So for every point, you can send it to minus of this point. Okay, and in particular for abelian surface, I can take the quotient of this abelian surface by Z mod 2. Okay, so it's a classical thing to see that actually there are 16 points where this action gives you this quotient becomes singular, and there are actually 16 nodes at those 16 points. So in particular, in this situation, I can resolve the singularity, and that's going to produce a K3 surface, which is usually known as the Kummer K3. The Kummer K3. Okay. And the resolution, the blow up of the 16 nodes actually gives me 16 exceptional divisors. Give me the 16 divisors inside this S. Okay, and this is actually the classical story that happens on the variety. Well, so what happens on the categorical level? So the first thing is actually maybe I'll state this thing as a small instance of this more general result of Bridgeland, King, and Reed. That's relating the kind of the geometric quotient with the kind of a categorical quotient. So if I take the derived category of the abelian surface, and I put actually equivariant structure on this corresponding to this Z mod 2 action, that's really equivalent to the derived category of this K3 surface, of this Kummer surface. Okay, where here this thing means the equivariant category. Okay, let me very quickly just try to explain. So what's really this equivariant category? So basically, it's a category where the objects are all the equivariant objects and all the morphism respect the structure. So object inside this category is really just an object inside the original category D of A, together with the equivariant structure, this phi here, where this phi is actually an isomorphism from E to this -1 upper star of E. It's an isomorphism from E with this involution. Okay, such that this is compatible with the group action, and in this situation, this means that if I compose phi and -1 pullback of phi, this will become identity. Okay, it's really just an equivariant object. And so what's the morphism in this category? Well, the morphism in this category are just any morphism that would respect this. So for example, this would be actually a morphism from E to F, such that, so if I use this phi to map it, so if I use phi E to map it to the pullback of phi, and here I use phi F to map it to the pullback of F, so here I have actually a, yeah, right. So here I have the -1 pullback of F, and I need this diagram to actually commute. Okay, so it's actually a morphism from E to F that's going to commute with these equivariant structures on the two sides. Okay, so very roughly, the category at least consists of this kind of object. I mean, for the people who know more about this thing, I should say that this is not quite enough for my purpose. I need some kind of enhancement of this action. So I really need this thing to be actually suitably enhanced. But let me not really get into the detail of the correct definition of equivariant categories. Okay, yeah. So this is actually the kind of the categorical thing. So this quotient becomes actually equivariant on category. Okay, and inside this, in this situation, actually there's a residual action. So there's a residual action. So I'll just define mu2 to be the Helm from Z mod 2 to C star. Maybe I should write C cross. Okay, so this is just the dual of this Z mod 2. So I claim there's actually an action of this mu2 on this equivariant category. So on this dA, which is, sorry, on this equivariant category, which is equivalent to ds. Okay, and this is actually very easy to understand. So this is really, in this case, just sending this E together with this equivariant structure to the one with the minus sign. Okay, I have this isomorphism, I just put a minus sign there. This is really just concretely how you should think about this thing. Okay, so I mean, whenever I have equivariant category, there's the action of the dual of this group on this equivariant category. Okay, and so in some sense, this is really the first categorical miracle that if I really work with variety, I wouldn't say. So this is first due to allergen, and the version I'm using here is actually some refinement of that due to Bayer, Perry, and maybe some other people. So the thing is, like, on this equivariant category, I have this mu2 action, this residual mu2 action. So if I take the mu2 equivariant category on this ds, that's going to just recover the original dA. Okay. If I take the mu2 equivariant category, it's going to send back to the original category dA. So on the geometric level, this Kummer K3 is a quotient of the abelian surface. But on a categorical level, each of them is a quotient of the other guy. One quotient is just by the Z-mod2 action, and the other quotient is by the mu2 action. And when I say quotient, I really mean take the equivariant category. Okay. This is really the kind of the first kind of really categorical miracle, I would say. Like in this situation, I can describe the abelian surface using the K3. Okay, you may wonder, okay, so I'm having like a involution of the derived category of the K3. So can we really write down so what this involution is? The answer is yes. So this is actually written somewhere in a paper by Beckman and Alberich. So this mu2 action is generated by something I'll call the IS, where this IS has a rather complicated formula. So this is actually the tensor with the ramification, basically. This EI are the 16 exceptional divisors. I take the sum of all of them because these are the ramifications. So half of this is still integral. So I tensor with this thing and then compose with just some autoequivalence called spherical twist with respect to the line bundle that's supported on this EI, on this exceptional curves. Okay, so ST here means the spherical twist. It's like an autoequivalence of K3 that can be done using spherical objects that just look like this. Okay, so I mean, if you look at this thing, you see that this autoequivalence, this evolution is actually kind of complicated. Okay, yeah. So now I'm reversing this direction of the equivalence. So the the derived category of the abelian surface is now described as an equivariant category on some K3. And remember, my goal is I want to deform this abelian surface in one more dimension. And so then this is actually the very nice idea that was originally proposed to us by Laura. So the idea would be, okay, I'll just deform this derived category of the abelian surface by deforming this K3 surface S. Now I really mean I'm deform this as an actual K3 surface together with the mu2 action on the derived category of this K3 surface. Okay, so I want to find one more direction that I can deform the K3. This is okay. I mean, the K3 deforms in 19-dimensional family, so I can deform in many other directions. But I want to find one additional deformation such that this mu2 action will deform together with the K3 surface. And if that were the case, then I can take the equivariant category. The equivariant category will just be very, will be actually just at the end giving me my non-commutative abelian surfaces. Okay, so this is actually just somehow the key idea. So this is what I'm going to try to explain in the next section. Okay, are there questions?
Kind of curious, I mean, how much of this equivariant business really uses anything to do with the Kummer K3? I mean, if you just took an abelian variety and modded out by the -1 map, you know, could some of the equivalents work in that case without?
That's a very good question. I don't know the answer. Even this BKR becomes like a tricky thing. So you may not have a very nice description of the equivariant category. And also, as you will see, I'm using a lot of things that, you know, are fairly nice for K3 surfaces. We understand very well how they deform, and we understand very well how to control their derived category, stability conditions. So all this become question mark in higher dimensions. Yeah, it's a very good question. I wonder about this thing at a certain point, but I don't have a good answer. Okay. Okay. So yeah. So the next thing I want to explain, like how the. So I'm gonna actually deform this deformation of the derived category of a K3 surface plus this mu2 action. Okay. So how do I do this? Well, there are some kind of machinery that allows me to abstractly deform a triangulated category or this kind of mu2 actions. Okay, so let me introduce the important notation. So I'm going to define K tilde to be the -1 eigenspace, of this mu2 action acting on this act on the triangulated category. So in particular, it's going to act on the total cohomology of this K3 surface. Okay. Yeah. So I'm going to just define this thing called K tilde. So this is something easy to calculate. I mean, especially you can already see the formula of this IS. Okay. So let me just give you some quick property of this thing. This is actually rank 16. This is a negative definite. Okay, and if you want, I can even write down a basis of this. This is actually generated by object by classes of this form, and but this is not really an integral basis of the lattice. So I take the one generated by this, and I take the saturation. So that's going to give me this K tilde. Okay. Yeah. So this is my K tilde, and so the key tool that I'm going to apply, I'm going to rely on, is the following result due to Eddington-Thomas. And also part of this is based on the work of Tolde and also Huybreis, I think. So given a deformation of S, then this IS, this involution, so IS is the generator of this mu2, so it's the involution. This IS deforms if and only if this K tilde remains algebraic. Yeah, so this is actually if and only if. So basically, I'm looking at the -1 eigenspace of this action on the cohomology. So if this -1 eigenspace is always going to remain algebraic when I deform this K3 surface, this is kind of like a variation of Hodge structure type of question. Then in particular, I know this involution on the level of category will actually deform together with this family of K3. Okay. Yeah. So this is actually one of the key tools that we are going to use to deform this IS. Okay. And more, let me actually just maybe mention a fact. So if I look at the total cohomology of this K3, inside here, I can take the perp of this K tilde. Okay. So this is going to be identified with the even cohomology of the abelian surface with Z coefficient. Okay? So the K tilde is actually the -1 eigenspace. Its orthogonal will be actually the +1 eigenspace his will survive under this equivariant category and become actually the cohomology on the abelian surface A. And remember here, I have these two things, V and W, that will have to remain algebraic. Okay? One of the part of my main theorem, this has the statement that when I deform this in this four-dimensional family of triangulated categories, I want V and W to remain algebraic. Okay. So now I have two types of things that has to remain algebraic under this deformation. The first is this K tilde. So minus one eigenspace to make sure the involution deforms. And in addition, I need this V and W, which is in the orthogonal of K tilde, to remain algebraic. To even at the end of the day allow me to talk about the moduli of class V, and W will give me the polarization and things like that. Okay, so I have all those things that's kind of have to remain algebraic. So let me maybe just before I say what's the key construction, let me just give a toy dimension count. Let me just give a very toy dimension count. Okay, so if I'm going to take the general polarized K3, a general element in this 19-dimensional family, so what's algebraic? Well, so there's H0, that's for sure algebraic. There's a polarization that has to be algebraic. And there's H4. Okay, and the general one would have Picard rank 1. So in particular, these are the only things that's algebraic. Okay. On the other hand, we know the deformation of this kind of K3 is actually happens in the 19-dimensional family. Right. 22 minus 3. So it's always something like this. Okay. And now in our case, okay, so what I need to be algebraic? Well, I need this K tilde to be algebraic. And in its complement, in its orthogonal, I also need V and W to be algebraic. So this K tilde, as I told you, is actually rank 16, generated by those things related to EI. And plus V and W, I have actually a rank 18 lattice. That has to be algebraic. And that's going to restrict my deformation to be inside a four-dimensional family. Right? It's 22 minus 18. So it should work. This should work. Right? I mean, if I only ask these classes to be algebraic, then I would be able to actually deform my K3 in a four-dimensional family. K tilde is algebraic means actually the involution deforms with it. I can take the equivariant category. Inside there, I will be able to take the image of V and W, and everything will work. Okay. There's a but. But if you think about this thing, the thing is like even in the K3 case, I already see that I need something like H0 and H4. Okay, so if I deform a K3 surface where these 18 things actually remain algebraic, then I need actually the H0 and H4 to be contained inside this rank 18 lattice. And it's easy to calculate, you know, like if you choose like a, you know, a bad V and W, then you know, if you choose basically just any V and W, then there's no chance that this H0 and H4 happen to lie inside here. Okay, so what do we do? So this is maybe the most technical part of my talk. So basically this is the second kind of categorical miracle here. So before everything, let me start a little lemma. Okay, so I have this K tilde, I have this V and W. So these are the things I needed to be algebraic. And let's actually maybe take the saturation, the lattice generated by this. Okay, inside here, I know I need something that looks like H0 plus H4 of a K3. And if you look at the intersection parallel on that thing, that's going to give me a hyperbolic plane. So usually I call this thing U. So inside here, I need some kind of hyperbolic plane. And the claim here is like, actually, you can embed a hyperbolic plane in this rank 18 lattice for any V and W. And in this case, the orthogonal will be actually something I call the lambda. And I can compute, for example, the signature of this lambda. So this K is negative definite, and V and W, you can verify they are both positive definite, and they are orthogonal. So the left-hand side is of signature 216. The hyperbolic plane is of signature 1, 1. And what remains here, this lambda, is of signature 115. This is just the easy lattice theoretic calculation. So why do I need this? So this is really the second kind of categorical miracle, or the flexibility that I get. So this is actually a result due to Mukai, maybe even from the 80s or something. So the claim is that I started with some Kummer K3 with a specific involution and V and W. But the thing is, like, I can find actually a full Mukai partner. So I can find another K3 T whose derived category is equivalent to the derived category of the Kummer K3 I started with. Such that inside this T, if I look at H0 plus H4, this is going to be corresponding to the hyperbolic plane inside this. So inside on S, I have all these classes. In particular, in the lattice, I have this hyperbolic plane. But I can always find a full Mukai partner such that this hyperbolic plane is rearranged to H0 and H4 of that full Mukai partner T. Okay, so I can actually achieve this. And when achieving this, that in particular also tells me, so where does lambda go? Now this lambda is actually sent to be into the orthogonal of this U. So in particular, this lambda is actually sent into the algebraic part of this T, the second cohomology, the H2 algebraic of this T. Okay, so another way to say this, so I would be able to find a full Mukai partner of this S. They have the same triangulated category, the derived category, and this T in this situation is really a lambda. This is the term is the lattice polarized K3. Okay, yeah. So I'm actually rearranging this thing so that actually this rank 18 lattice will already contain H0 and H4, and another signature 115 lattice inside H2, which is somehow my lattice polarization of my K3. And just because this triangulated derived categories are equivalent, I'll be able to translate my, so let me call this phi, yeah. I'll be able to translate my involution on the D of S using this derived equivalent. I can make it into actually involution on this T. Okay, and just basically by my definition, so this guy will deforms with actually a lambda polarized deformation of this T. Okay, since in order for this IT to deform, in order for this guy to deform, it just means like in the definition of this T, I need a -1 eigenspace to actually deform with it. But the -1 eigenspace of this comes from actually the -1 eigenspace on this S, which is exactly contained inside this U and lambda. So this is really how I chose this U and lambda. So their direct sum contains this K tilde. Okay, but this is actually the second kind of categorical convenience. Using passing to actually another model without changing derived category, I would be able to really arrange this -1 eigenspace into H0 plus this middle thing plus H4. Okay, so yeah, so this is actually the second part. This is really the key the key observation. Somehow I will be able to really deform it. Okay, and for the rest of this will be actually just a kind of a straightforward thing. So take a K3 surface, maybe I'll call this thing TB or something, in this four-dimensional family. So when it's polarized by a signature 115 lattice, this thing will deform in a four-dimensional family. So in this four-dimensional family of lambda polarized K3 surfaces, And I know by my construction, there's actually deformation of the mu2 action on this. This deformed mu2 action. There's a mu2 action on this derived category of this TB. Then I would define my AB to be the derived category of this TB with the mu2 action. mu2 action. Okay, this gives me my non-commutative abelian surface. Yep. Okay. Of course, there are many more things we have to do here. We need to construct the stability condition, which is not too difficult, and then we need to say a lot of nice thing about the moduli space, which come down to the fact that actually I'm looking at the moduli space over a family of Calabi-Yau2 category. So the moment one fiber is non-zero, then in particular all the fibers will be non-zero. So this morphism, this moduli space relative over the base is a smooth family. Okay. Yeah. So, but let me not really go to all these technical details. I think maybe I explained the two key ideas and how the triangulated category allows me to really do all the things. Okay. Before I move on to Wei-type abelian fourfold, let me see whether there are questions.
The card number of the abelian surface, like, does that have any sort of more refined picture in this setting, or?
Yes. So basically, for abelian, so now instead of thinking Picard number, you should think the total algebraic lattice of the derived category. So for generic abelian surface, it's going to be H0, the line bundle, and H4. So it's rank 3. And will deform to a generic fiber in this 4-dimensional family. It will become 2. So in particular, it's really only generated by V and W. Yep, that's right. And I should say that this is not really a kind of a very kind of a weird picture. So there are similar things happens. For example, you take the cubic fourfold. Inside this derived category, there's like a semi-orthogonal component, usually known as the Kuznetsov component. That's like a case-3 type of thing. This is a case-3 category. So cubic fourfold deforms of 20-dimensional family. And generically, this case-3 category is of numerical rank 2. But there are 19-dimensional locus where the algebraic lattice is rank 3, and even like this case-3 category becomes the derived category of the case-3 surface. So the case-3 surface also allows this kind of non-commutative deformation. Yeah. So it's just like we never saw kind of a non-commutative deformation of abelian surfaces arising as a semi-orthogonal decomposition in any kind of meaningful way. So this construction is partially motivated by we don't really see similar picture of abelian surfaces. Yeah.
So can you actually describe the 3-dimensional locus that comes from the construction of generalized Kummer 4-dimensional?
That's a good question. I would expect there's already, so I think one easy way to say this is that the moment you have actually a square, let me be careful about the number. The moment you have a square 0 class, I think it's already a twisted abelian surface. And if you have actually another class that intersect this into 1, then that's actually an actual abelian surface. Yeah. So I'm just saying, like, somehow lattice theoretically, you would be able to determine the same.
Okay, thank you.
Yeah.
Sorry, may I ask a more elementary question?
Yeah, sure.
What's the relation between deformation, maybe history surface, and deformation of the derived category itself? I'm just wondering why not just deform the abelian variety, then consider what's the problem, or what's
Yeah, so basically the problem is like the abelian surface only deforms in 3-dimensional family, but I want additional family. And so K3, the benefit of working with K3 is like it deforms a lot more. And with all the things I said, you'll be able to even deform the involution a little bit more than 3, actually, one more than 3.
So deform and a real family always produce an deformation of derived category, but converse is gives us new things.
That's right. So another way to say this thing, you can actually compute the Hausdorff cohomology of the derived category of abelian surface, or K3 is the same. So there you already see like somehow it's suggesting that there should be actually one more direction. And this Hausdorff is really some kind of, it controls the deformation of categories. So somehow if you compute it already there, you can see like there should be one more direction. That's deforming the category, but not coming from H1 of the tangent space of the underlying variety. There will be actually another motivation of this question. Yeah.
Yeah, thank you.
Good. Okay, so eventually let's get to this.
Sorry, so the
Yeah,
name
go
of
ahead.
the cohomology you just mentioned, is it Hochschild or Hausdorff? Is it what?
Hausdorff.
Hochschild.
Hausdorff, yes.
Ah, okay, sorry, okay.
Yeah, that's
I
right.
wasn't sure. Okay, thanks.
Yeah. Okay. Other question? Oh, good. Okay, so V type abelian fourfold. Okay, let's see. Before I get into the details, let me actually maybe just come back to the abelian surface situation and try to just give you the picture here. So sometimes actually this picture becomes more clear when we get to the non-commutative abelian surface. But let's start with abelian surface. Okay, so let's say I take the derived category of abelian surface, so the abelian surface. Okay, so in this situation, this A cross A dual plays 2 different roles. Okay, so the first thing is that this is actually the Abnesi variety of my moduli space. Okay, this is the thing we started from the beginning. I take this moduli, I take the Abnesi morphism, and I can take the fiber. Okay, so this is the first thing. And the second thing, which is more categorical, so this is actually the identity component of the autoequivalence group of this triangulated category. So alt EQ means autoequivalence of this triangulated category D of A. Okay, so there's a natural kind of algebraic space structure on the autoequivalence, and then you take the component of the identity. This is really A cross A dual, and this is easy to understand. So A acts as translation, and A dual acts as tensor torsion line bundles. Okay, then in particular, this is the identity component of the derived category. Okay, so for any V, if I fix this class V, so this 2 interpretation induces actually a map. So this induces a map. Okay, so I'll call this map MV, so this depend on V. So to start with, I take this A cross A dual, and here I'm thinking about this thing as the autoequivalence of this D of A. Okay, so just because this is autoequivalence, this is gonna just act on the moduli space. But then in particular, if I fix a point inside the moduli space, so that's gonna actually give me a morphism from A cross A dual to the moduli. Okay, so for example, this can be given as send the object element A here to the action of this A on some object. Okay, so let's say maybe this E is a fixed stable object, a stable sheaf or something. Okay, so this is going to be actually inside this moduli of stable sheaf. Okay, and it's easy to see that either I translate this sheaf or I tensor torsion line bundle that's still stable of the same character. So this A cross A dual actually just maps to this moduli space once you fix a point. Okay. On the other hand, this is the thing we started with. So there's an Abernoisi morphism that's also mapping to A cross A dual. So, and here this A cross A dual is viewed as the Abernoisi of the moduli space. And I can take the composition of this thing, and this is what I call MV. Okay. It's a very good exercise to convince yourself that if you view this as just an abstract morphism from A cross A dual to itself, this thing depends on the choice of V. Okay. If you choose different thing, like say, for example, 1, 0, n, or different n, this will actually just look like a different morphism. And if you take a torsion shape, like 0, a curve 0, something, that will be just a different morphism. Okay, so this is actually the kind of the interesting thing that we should keep in mind. Okay, this is actually just an example, like a warm-up. What happens for abelian surfaces? Okay, so before I say the everything, let me actually just define what I mean by abelian fourfold of V type. Okay, so let's say abelian fourfold called this gamma is of V type. If the following is true, there's actually the following ring has an embedding into the endomorphism of this gamma. Okay, so in particular, you have actually the image of square root of minus d. That just means like you have an endomorphism of gamma whose square is actually minus d times the identity. So it's like multiplication by minus d. Okay, d is a positive integer. Such that the generator, so basically it's the square root of minus d. This is a concrete endomorphism of gamma. So in particular, this thing acts on the H10 of this gamma, and I just need this small condition. This acts on the H10 is equal dimension eigenspaces. So there will be two eigenspaces of the eigenvalues plus or minus square root of minus d, and I need these two eigenspaces to have the same dimension on H10 of gamma. Okay. So you don't need to worry too much about this technical condition. So basically the key upshot is like, this is the thing that has some kind of weird endomorphism. It has some kind of additional endomorphism, like a square root of minus d. Okay, so what's the connection between this story and our non-commutative abelian surface? Well, here's the story. So for a non-commutative abelian surface, maybe I'll just still call this thing AB. Okay, so I'm going to draw a picture, and maybe let me just draw it on the next page. So on the one hand, I can take the autoequivalence of this triangulated category and take the identity component. This still makes sense, and this indeed once again going to be an abelian fourfold. So this relies a little bit on some kind of deformation theory, but you can check this is still an abelian fourfold. Okay. So remember, for this abelian surface, non-commutative abelian surface, I had two classes, V and W. So far, I have been always using V to form the moduli and W to give me the polarization. But there's no reason I have to do this. I can just swap these two things and form the moduli with W. Okay. So in particular, if I just run the same construction as before, this autoequivalence will map to the moduli space with respect to, for example, V. And then I could compose this with the Abernoisi. So this gives me actually a morphism, Abernoisi variety from the autoequivalence to the Abernoisi variety. Either V or W. Okay. Sorry, this is W. I want to use the two characters to write down two different things. Okay, so I can do this thing for V and I can do this thing for W. But that gives me actually two different morphisms. Okay, well, And it's not too difficult to really verify that they are both actually isogenous. So in particular, I can compose, for example, MV with MW inverse. So it's an isogeny, but then up to a multiple, I can really invert this thing. Like if you want to think about this thing on H1Q. So this makes this abelian. So basically, I have a composition. So this gives me an endomorphism in my definition from the Abernethy to itself. Okay, so the way I'm writing this thing, it's actually endomorphism from this Abernethy variety to itself. But this makes this abelian variety, this abelian fourfold of Wei type. Okay, so what I mean by this is like if you write down this endomorphism and take a square, this thing is really minus d times identity. Okay, and indeed, actually, in this situation, you can compute this d. This d is given by the basically the v squared times w squared. Okay, so the square here is given by so-called Mukai pairing. Okay, yeah. So this gives actually, in some sense, a transparent proof of why this abelian fourfold associated to the generalized Kummer variety or the intermediate Jacobian has actually Wei type structure. So it's really coming from that you write down this morphism depend on using one of these two characters. They're not the same, and then when you compose them, you really get a Wei endomorphism. Okay, and in some sense, actually, for abelian surface is slightly confusing since for abelian surface, actually, these two things are iso. Even though the morphism will depend on V, but actually these two things are abstractly iso. Well, indeed, for general non-commutative abelian surface, it's not the case. They are really just differ. They'll differ by isogeny. This somehow for sure has to happen. Okay. Yeah. So this is actually the thing, and the proof is really just do the deformation and reduce it to the abelian surface situation, and from there you can actually see everything clearly. Okay. Yep. And finally, I think I mentioned a little bit this Hodge conjecture, this work of Markman, the first work of Markman on Hodge conjecture for this type of abelian surface. So let me actually just say a little bit about that. So for this Hodge conjecture for Wei type abelian fourfold, let me briefly say the thing. So okay, so for a general Wei type abelian fourfold, the interesting thing would be, of course, looking at the Hodge classes in codimension 2. So it's actually H22 gamma Z. So this thing, it turns out to be actually three-dimensional. So there will be actually the polarization squared, but there are two more classes. Okay. But indeed, in this situation, there's some kind of big symmetry. And at the end, you just need to actually prove the algebraicity of one additional class. Algebraicity of one additional class up to the endomorphism of this gamma action. Okay, so usually people call this class, choose a specific one called Cayley class or something. So there's an additional class that you have to prove is algebraic to verify the Hodge conjecture. Okay, so from here, what Markman did is the following. So he started with actually the case of generalized Kummer, so the ones from actual abelian surfaces. Okay, so I have actually A cross A hat that's embedded into the moduli space of sheaves of class V. On this moduli space, you actually can construct some natural sheaves. You can construct some natural sheaves on this moduli space that's constructed out of the universal family of this moduli space. using the universal family. Okay, you can construct this. And if you take the second term class of this, so this is precisely going to give you the class, the so-called Cayley class, the class that we need to prove the algebraicity of. Okay. Yeah. But this is actually the situation of the for generalized Kummer varieties. So the second term class is of course algebraic. This natural sheaf is actually a nice coherent sheaf. So you get an algebraic class, and you can just take you can actually verify the algebraicity of the Cayley class. Okay. So from here, you know this conjecture, Hodge conjecture on three-dimensional locus, but then you have to deform it to all the to generic Wei-type abelian fourfold. So what Markman did for the rest of this proof is like then he used actually deformation of some special thing that exists in the hyperkähler world. So he used this thing called the deformation along twistor line. Okay, so this is actually going out of the algebraic category. So this is really deforming the hyperkähler variety, the hyperkähler manifold as Kähler manifolds. You deform it to something that's really only Kähler. So there's a twistor line, and then there's a theorems from complex geometry telling you, so this kind of sheaf will actually deform together with your twistor line, and your twistor line is actually covered the whole moduli space of Kähler manifolds that's arising from deformation of hyperkähler. So from here, you can just go along twistor line to come back to other points in this four-dimensional family. And that's how this thing is proved. So in particular, we need a bunch of differential geometric ingredient to really do this. But now with all the things I developed, so now with the story of non-commutative abelian surfaces, with this non-commutative abelian surfaces, we can prove this thing directly. Maybe I'll just say it this way. So basically now the upshot is like you see that the autoequivalence, the identity component of the autoequivalence group is once again mapped into the moduli space on this non-commutative abelian surface of this class V. Okay, and this moduli space will actually come naturally in a four-dimensional family. So on which I have actually the universal family of stable objects. So whatever you can do on the abelian surface case, it just immediately deforms together with this moduli space. So this is actually all well defined on the four-dimensional family. And just because on the abelian locus, I know this is actually giving me the correct class. So when I deform this, I actually know that. So everywhere, so actually generically, this gives me the algebraic, the algebraicity of the Hodge class in question. Okay, so in some sense, one application of this story is like is interpreting this association between the Kummer type manifold and this abelian fourfold with of Wei type in more kind of moduli kind of way, and it gives you like a more algebraic proof of the Hodge conjecture in this case. But I should mention that all the abelian fourfolds arise this way will have discriminant 0. There's some invariant of the abelian fourfold of Wei type called discriminant, and all the things we got here are of discriminant 0. So in particular, for all those things of the other Wei type abelian fourfold of other discriminant, this method doesn't really tell you how to prove the Hodge conjecture. But Markman already has the proof there by passing to abelian sixfold of discriminant 0 and then using like a kind of a classical degeneration type of argument to reduce back. Okay. I think I'll just stop here. Thank you.
Thank you, Xiaolei. So are there any questions or comments? So like at the beginning, you kind of mentioned the third intermediate Jacobian.
Yeah, right.
Yeah, so
That's right. It's actually not too difficult to see the third intermediate Jacobian and the Abenezi are isogynous to each other. Yeah, and this of way type thing, it's preserved under isogeny. And also the Hodge conjecture is equivalent under isogeny. So basically, you can, if you proved anything for one abelian fourfold of way type, that's all immediately true for anything that's isogynous to this. Yeah.
I
So
see. Okay.
this is why at the beginning I was saying more about this intermediate Jacobian, which is how O'Grady originally introduced all these things. But at the end of the day, it's basically the same story as thinking about the Abenezi variety, for example.
So these intermediate Jacobian are also of discriminant 0.
Yeah, they are all discriminant 0.
See.
I
I see.
don't know how to get something not discriminant 0 in this picture.
I see. Thank you. Are there any more questions? Okay, if not, then let's thank Charlie again. Thank you very
Thank
much.
you.